A talk will be given by early career invitee Dr. Carla Perez from University Sao Paulo, followed by our main talk speaker, Professor Ana Ramirez from Universidad Industrial de Santander. And Professor Chris DeCourt from Radboud University Medical Center will moderate this session. Questions can be asked in English, Portuguese, or Spanish. The organizers of the webinar series will be able to translate your questions into English for the speakers to answer. Please type your questions in the Q&A box in the chat box at any time. They will be answered during the question and answer session of this webinar. Automatic closed captioning is available. Please press the closed captioning button and choose show caption to enable it at any time during this webinar. I would now like to introduce you to the organizing committee of the webinar series. Latin America Outreach Initiative Chair Hermes Kamimura is an associate research scientist at Columbia University in New York. He is a member of the Volunteer Engagement Committee of the UFFC Society and general co-chair of the Latin America Ultrasonic Symposium. Today, Hermes will be announcing some of the Latin America Outreach Initiative activities and helping translate questions posted in Portuguese during the question and answer section. Volunteer Engagement Committee member Sophie Morse is a research fellow at Imperial College London. She is a member of the Volunteer Engagement Committee of the UFFC Society, as well as the Diversity and Inclusion and Women in Engineering Chair for the Latin America Ultrasonic Symposium. Sophie will be introducing our speakers today. Latin America Outreach Initiative member Andrea Pulido is a PhD student at KU Leuven in Leuven, Belgium. She is a volunteer student on the Latin America Outreach Initiative. Andrea will be helping with translations for Spanish questions during the Q&A session. And lastly, we have Latin America Outreach Initiative member Stephen Lee, who is a PhD student at Columbia University in New York. He is a volunteer student on the Latin America Outreach Initiative, and Stephen is helping with audio and video editing for our webinar series. And now, Hermes.
Hello, everyone. We are delighted to introduce you to this webinar, America Latina in Foco. It's our very first activity in the Outreach Initiative, and our goal is to increase the participation of Latin Americans in the UFFC Society. It's also an excellent opportunity for the rest of the society to meet these great early career and senior researchers from Latin America. And this webinar was organized with the help of Miguel Bernal, Theo Pavan. They are also in the organizing committee of the Latin America Ultrasonic Symposium, and also by the Volunteer Engagement Committee Chair, Kendall Water, Education Chair, Ruo Cheng Lu, and of course, with the great help and encouragement of the President of the Society, Paul Reynolds, who is here. Paul, if you want to say a few words, it's up to you, or you can also speak in the end. You can type in the chat. And of course, I want to thank Ana and Carla and Chris for being the panelists in this webinar. And we are open to other topics. We are in touch with Eckhart and Jacob Jones to get also speakers in ferroelectrics and frequency control. If you know someone you want to see here speaking, please reach out to us. Can you put in presentation mode, please?
What was that?
The presentation mode for this, just
Yeah.
to increase a little bit. Yeah. So we have also planned this Latin America Ultrasonic Symposium in October 4th and 5th. And this will be a great networking activity. So please join us. Please, next slide. 2 weeks later, we have the summer school, Transducer and Waves. And this designed primarily for Canada and Latin America. So students from this region will be able to learn the pillars of the acoustical imaging, and reach out to Koen van Doggen if you want more information. Next slide, please. And finally, I want also to alert the Latin American Fellows about this opportunity, the Star Ambassador Award. And this award provides up to $2,500 for members to travel and give talks and represent the society in different institutions. So we highly encourage the participation of Latin Americans. And yeah, this is it for the announcements. I just want to say also, if you are interested in volunteering any UFFC activities, including Latin American activities, You can contact us through the website. You can see in the main website of UFFC a tab for volunteer engagement. Please see the information there and reach out to us. And I will hand it over to Lacey to continue that. Thank you.
Thank you, Ramirez. I have some poll information that we were going to share with everybody. If you could please participate, that would be very appreciative. And then as you're completing the poll, we're going to have Sophie introduce Dr. Carla Perez.
Hey, so it's with great pleasure that I introduce you to our first speaker of today's webinar. It's Carla Perez, and she's a researcher in the dermatofunctional evaluation and intervention laboratory at Ribeirão Preto Medical School in the University of São Paulo in Brazil. And Carla actually did her undergraduate in physiotherapy and then her master's and PhD in health science at the University of São Paulo. And she did a collaborative period at the University of Lisbon in Portugal as well. And her current work focuses on using ultrasound as an imaging technique to assist in the diagnosis of lymphedema in breast cancer survivors, which we'll hear more about now. So with that, I'll let you enjoy her talk. Thank you.
Thank you all. We're going to play Carla's talk in just a moment.
América Latina en Foco.
Olá, meu nome é Carla Perez, sou fisioterapeuta, membro do Laboratório de Avaliação e Intervenção em Dermatofuncional da Faculdade de Medicina de Ribeirão Preto, Universidade de São Paulo, mesmo local onde eu fiz toda a minha formação da graduação ao doutorado, e vou apresentar o tema Lymphedema e Survivors of Breast Cancer. Os tratamentos cirúrgicos e adjuvantes do câncer de mama podem trazer algumas morbidades. O linfedema de membros superiores é uma das mais recorrentes e mais preocupantes. O linfedema ele afeta o membro superior homolateral ao tratamento cirúrgico, é resultado de danos ao sistema linfático e sanguíneo e caracterizado como um acúmulo de líquidos no espaço intersticial, causando dessa forma um edema crônico. Além da disfunção circulatória, outra característica muito evidente do linfedema é a fibrose tecidual, tanto de pele quanto de tecido subcutâneo. Com relação às estimativas, elas mudam dependendo da abordagem cirúrgica. Na linfadenectomia axilar, que é retirada de parte ou de todos os linfonodos da axila, essa variação fica entre 14% e 40%. Já na abordagem com linfonodo sentinela, essa incidência cai para 6% a 10%. Nosso grupo de estudos atua num centro de reabilitação em mulheres que passaram pelo tratamento do câncer de mama, que é o REMA, e nesse local foi feito um estudo coorte retrospectivo de 10 anos para levantamento da porcentagem de linfedema nessa população. Das 792 mulheres que foram atendidas nesse período, 296 tinham linfedema, ou seja, 38% da população. O risco de desenvolver linfedema assola sobreviventes do câncer de mama por um longo período pós-cirurgia Isso porque o tempo de surgimento é incerto e pode variar de meses a anos. Atualmente não existe uma maneira precisa de distinguir pacientes com probabilidade de desenvolver linfedema. O que há são fatores de riscos bem definidos, que incluem a dissecção dos linfonodos axilares, a radioterapia principalmente envolvendo a axila, alto índice de massa corpórea e uma predisposição tanto genética quanto circulatória prévia. A avaliação e diagnóstico do linfedema é essencialmente clínica. Ela é realizada por meio de palpação manual e também da medida da volumetria. O volume do membro é considerado padrão ouro para a medida de edemas irregulares e pode ser realizada tanto de forma direta quanto indireta por meio da perimetria. No entanto, os resultados variam amplamente porque depende de estimativa subjetiva dos avaliadores. A perimetria, que vai dar o cálculo do volume do membro, ela pode ser insuficiente com relação às informações, já que se ocupa apenas em descrever um formato externo do membro, não considerando as alterações intrínsecas dos tecidos afetados. O diagnóstico exclusivamente clínico do linfedema não aponta limiares consistentes para a diferença entre os membros superiores ou ainda entre avaliadores. Por isso, observa-se um número crescente de técnicas e instrumentos usados para o exame objetivo do linfedema. Alguns desses vão se ocupar e mensurar a circulação linfática ou sanguínea, dentre eles a linfocintilografia tem um destaque e é considerada um padrão ouro e teste confirmatório para linfedema. No entanto, apenas a avaliação da circulação pode não ser suficiente, já que todo o tecido de pele subcutâneo também são afetados. Para avaliação tecidual, nós temos a ressonância magnética, que tem um alto custo e inviabiliza a utilização, e também a ultrassonografia diagnóstica. Embora as recomendações das diretrizes de diagnóstico do linfedema possam estar tipicamente atrasadas em relação a novos desenvolvimentos no campo diagnósticos, as mudanças nas diretrizes dependem de evidências robustas necessárias para a ultrassonografia. Certamente, as características do ultrassom, por ser uma modalidade não invasiva, pode tornar ele a primeira escolha para o diagnóstico do linfedema. Claro que a interpretação das imagens tem que ser feita por um profissional experiente com essa alteração. A ultrassonografia diagnóstica é uma ferramenta potencial para ver, avaliar e quantificar a composição do tecido do membro superior. Os primeiros estudos se ocupavam apenas em mensurar a espessura do tecido subcutâneo e pele, mas estudos mais recentes vêm mostrando alterações da textura de imagem. No nosso laboratório, em parceria com o professor Antônio Adilton Carneiro, do Grupo de Inovação em Instrumentação Médica e Ultrassom, realizamos dois estudos para mensurar o grau de comprometimento, a topografia e as alterações biofísicas do tecido subcutâneo do linfedema secundário ao tratamento do câncer de mama por meio de ultrassonografia diagnóstica, utilizando tanto o modo B quanto elastografia. Para isso, foram coletadas 42 mulheres com linfedema unilateral. O sinal foi coletado na região anterior do membro superior afetado e não afetado pelo linfedema nos 7 pontos pré-definidos. Para avaliação das imagens em modo B, cada imagem de ultrassom passou a ser definida como a região de interesse entre duas linhas ecogênicas, caracterizando dessa forma o tecido subcutâneo. Essas imagens passaram por processamento em ambiente MATLAB e também por meio do software ImageJ. Na ROI determinada foram implementadas medidas para espessura dessa região, entropia e ecogenicidade. Para a variável espessura, todos os pontos avaliados mostraram ter uma espessura maior do que o membro superior não afetado. Com relação à variável ecogenicidade, que é a capacidade do tecido em refletir um eco da onda de ultrassom, indicativo da densidade do tecido subcutâneo. O membro superior afetado pelo linfedema mostrou uma maior ecogenicidade também em todos os pontos, exceto no punho. Os achados, então, indicam que os dados apresentados foram consistentes, tanto na identificação quanto na mensuração do grau de comprometimento e das alterações biofísicas do tecido subcutâneo do linfedema. Já o segundo estudo teve como objetivo introduzir uma nova forma de avaliação do linfedema secundário ao tratamento do câncer de mama, utilizando então o modo elastografia, para propor uma ferramenta confiável para a mensuração da textura do tecido subcutâneo. Notem que a textura aqui está relativa à rigidez tecidual, que é uma prática muito comum da fisioterapia, avaliar a rigidez por meio de palpação manual, o que não garante dados mensuráveis ou não tem uma confiabilidade entre os avaliadores. O estudo foi realizado, então, em duas etapas. Primeiro, desenvolvimento e caracterização de um fântão com medidas conhecidas. Esse fântão foi o padrão de comparação de deslocamento do módulo de Young entre o tecido avaliado e o fântão. Então, ele foi um padrão. Todos os deslocamentos foram comparados a esse fântão de medidas conhecidas. E o segundo estudo da aplicação do protocolo dessas medidas num membro superior com linfedema e no contralateral. Foi utilizada a elastografia freehand e a comparação do módulo de Young de cada ponto nos mostrou que o membro superior com linfedema apresenta maior rigidez de vários pontos. Além disso, a região de antebraço mostrou-se a região mais comprometida, mais rígida, mais endurecida. A elastografia, então, com o fântão de medidas conhecidas, mostrou uma ferramenta válida para avaliar essa rigidez e utilizá-la no lugar da palpação manual, tendo dados mais quantitativos e uma melhor qualidade da avaliação. Agradeço a atenção de todos. Obrigada.
After that lovely talk from Carla, I'm now going to introduce our second speaker, Ana Ramirez. She's currently a full professor in the Electrical, Electronics and Communications Engineering Department at the Universidad Industrial de Santander in Colombia. She's actually completed her bachelor's at this university and then did her PhD in electrical engineering at the University of Delaware in the US. And she then did a postdoc at Delft University in the acoustical wave field imaging group. Her interests lie in the field of acoustic signal processing, applied to medical and geophysical data, where she uses full waveform inversion, compressive sensing, and sparse signal processing. And in her talk today, she's going to be discussing two different full waveform inversion imaging methods. And with that, I'll leave the floor to Anna. Thank you.
América Latina en Foco.
Hola a todos, bienvenidos a este webinar. Y la charla de hoy la he titulado Comparación de métodos para la generación de imágenes usando inversión de onda completa para la detección del cáncer de seno. Este trabajo fue realizado en conjunto con el Dr. Koen von Doggen de la Universidad de Delft y el Dr. Sergio Abreu de la Universidad Industrial de Santander. Mi nombre es Ana Ramírez y actualmente soy profesor de la Universidad Industrial de Santander. La formación de imágenes de ultrasonido del seno requiere que sea incluida la mayor cantidad de información posible medida en los transductores. Esto con el fin de generar imágenes de muy buena calidad que permitan la detección de cáncer en el seno. Las técnicas avanzadas para la formación de imágenes de ultrasonido, como por ejemplo la inversión de onda completa o FWI, usa toda la información medida, usualmente en un arreglo de sensores tridimensional, ubicados de tal forma que encierran completamente el seno. FWI usa la información de multiple scattering, dispersion and refraction, medido en los traductores de ultrasonido para generar una imagen. Esto permite que las imágenes obtenidas sean de mayor calidad o de mayor resolución si se comparan con las imágenes que se obtienen a través de otros métodos que solo usan información de las ondas que son reflejadas por el tejido. Adicionalmente, FWI no solamente permite mejorar la resolución y la calidad de las imágenes, sino que también permite obtener información cuantitativa de los tejidos bajo estudio, tales como velocidad de propagación del sonido en el tejido o la densidad del tejido. Esta información nos permite discriminar el tipo de tejido que se observa en las imágenes e identificar la presencia de un tejido canceroso. La inversión de onda completa o FWI es un método no lineal y puede ser implementado ya sea en el dominio del tiempo o en el dominio de la frecuencia. La implementación en cada dominio tiene sus pros y sus contras, y la selección del método de implementación depende de los requerimientos del problema que se desea solucionar. En esta charla discutiré acerca de las diferencias de las dos implementaciones. Una de ellas es la inversión en el dominio del tiempo que llamaré TDI, y la otra es la inversión en el dominio de la frecuencia o Contrast Source Inversion que llamaré CSI. Mostraré algunos resultados de las dos implementaciones para generar imágenes en 2D de un seno sintético, a partir de unos scans de ultrasonido que son medidos en un transductor circular que encierra completamente el seno. Presentaré algunas ventajas y desventajas de los dos métodos cuando los scans que son medidos tienen ruido o cuando se encuentran en un ambiente libre de ruido. También presentaré alguna discusión sobre las ventajas en el número de transductores que se deben usar en cada método, dependiendo si se usan como transmisores o como receptores. Por último, presentaré algunas conclusiones respecto a la complejidad computacional de cada uno de los métodos. Para el caso de la ecuación que modela la propagación de las ondas en el dominio del tiempo, se utiliza la ecuación de onda escalar con densidad constante. En este caso, en la ecuación usamos P haciendo referencia al campo de presión y S haciendo referencia a la fuente. Para el proceso inverso, se desea encontrar cuál es la imagen con la información cuantitativa de la velocidad del sonido en los tejidos del seno, formulando el problema inverso de tal forma que se busca la imagen solución que minimiza el error cuadrático entre los datos medidos y los datos modelados. Este problema se puede solucionar usando el método del gradiente descendiente o steepest descent. Este método iterativo requiere el cálculo de un gradiente que podemos obtenerlo a través del método del estado adjunto. Por otro lado, para el caso de la inversión en el dominio de la frecuencia, la ecuación que modela la propagación de las ondas en el dominio de la frecuencia es la ecuación integral. Y en esta ecuación utilizamos la función de Green. Ahora, en el caso de la propagación en el dominio de la frecuencia, el campo de presión total se formula como la suma del campo de presión incidente y el campo de presión dispersado. El proceso inverso consiste en encontrar la imagen de la velocidad del sonido que minimiza el error cuadrático en el dominio de los datos medidos, es decir, la diferencia entre el dato medido y el dato modelado, pero se añade una restricción adicional y es el error cuadrático en el dominio de la imagen. Con este método de Contrast Source Inversion se estima primero la fuente contraste y a partir de la fuente contraste se puede estimar la imagen de la velocidad del sonido. En los experimentos realizados, el primer resultado que podemos observar es la reconstrucción de la imagen del seno a partir del uso de 157 transductores como fuentes y 157 transductores como receptores. Primero, revisaremos la reconstrucción en un ambiente libre de ruido. Para este primer experimento, la reconstrucción en el dominio del tiempo arrojó un resultado con una relación señal a ruido pico o PSNR de 41 dB. Para el caso de la reconstrucción en el dominio de la frecuencia, usando contrast source inversion, si se usa únicamente una frecuencia para la reconstrucción, se obtiene un PSNR de 39.6 dB. Cuando se utilizan 31 frecuencias durante la inversión, se obtiene una imagen de mejor resolución con un PSNR de 40 dB. En el dominio del tiempo, los scans medidos y modelados fueron filtrados para tener únicamente el rango de frecuencias que son utilizados también en el proceso inverso en frecuencia. Sin embargo, la diferencia de 1 dB que se observa en los resultados obtenidos se debe a que en el dominio del tiempo se usa scans con todas las frecuencias dentro del ancho de banda seleccionado, mientras que en el dominio de la frecuencia solo se seleccionan 31 frecuencias dentro de este ancho de banda. Bien, el siguiente experimento consiste en determinar si los métodos siguen el principio de reciprocidad. Para esto, se probó la reconstrucción de la imagen del seno a partir del uso de 157 transductores como fuentes y 15 transductores como receptores. También se planeó la reconstrucción del seno a partir del uso de 15 transductores como fuentes y 157 transductores como receptores. En este caso, nuevamente la reconstrucción se hizo en un ambiente libre de ruido. Para este caso, la reconstrucción en el dominio del tiempo arrojó como resultado que el proceso de inversión satisface el principio de reciprocidad y de esta forma el proceso de diseño de un sistema de adquisición se simplifica dado que no es necesario utilizar una gran cantidad de fuentes para generar imágenes de buena resolución. Para la reconstrucción en el dominio de la frecuencia, se obtuvo que el método CSI no satisface el principio de reciprocidad y el método es más sensible a la cantidad de receptores que se utilice en el diseño de adquisición. Así, si queremos utilizar CSI como técnica para generar imágenes de ultrasonidos, el resultado de la inversión que me da una mejor calidad en las imágenes es aquel que utiliza un mayor número de receptores en el diseño de la adquisición. Ahora, en el siguiente experimento, los dos métodos se probaron en la generación de las imágenes cuando los scans se encuentran contaminados con dos diferentes niveles de ruido. En el primer caso, los scans se contaminaron con 1% del valor máximo de amplitud del scan sin ruido. Y la reconstrucción de las imágenes obtenidas para ambos métodos fue superior a 40 decibeles. Para este nivel de ruido podemos decir que los métodos son suficientemente robustos. Sin embargo, en el segundo experimento se le añadió una cantidad del ruido al scan cuyo valor de amplitud es del 2% del valor máximo de la amplitud de los scans sin ruido. Y para este caso, el método en tiempo aún es capaz de reconstruir la imagen, aunque se observa de menor calidad o más suavizado. El método de inversión contra source en frecuencia no permite reconstruir claramente la imagen y se observa mucho ruido en la reconstrucción. De hecho, en algunas zonas de la imagen no es posible diferenciar qué tipo de tejido se encuentra. La razón para este resultado es que para la inversión en tiempo se utilizaron todas las frecuencias disponibles, mientras que para la reconstrucción en frecuencia solo se invirtieron 31 frecuencias y con esta información el método de inversión contra source no es suficientemente robusto al ruido. Para obtener un resultado más comparable entre ambos métodos, se debe invertir todas las frecuencias disponibles en el método de contra source inversion. Para finalizar, quisiera mencionar algunas conclusiones respecto a la complejidad computacional de los dos métodos. Hemos visto que el método de inversión en tiempo es robusto a la generación de imágenes en un ambiente de ruido y presenta ventajas cuando se desea diseñar la adquisición con un número limitado de fuentes y receptores, dado que el método satisface el principio de reciprocidad. Sin embargo, la principal desventaja de este método es su alta complejidad computacional, debido a que el cómputo de los campos de presión en el proceso de modelado puede ser hasta 1000 veces mayor que el cómputo de los campos en el dominio de la frecuencia. Esto se debe a la estrategia de discretización de la ecuación de onda en el dominio del tiempo. Esta diferencia ocurre porque es necesario cumplir con la condición de estabilidad de Courant. También hay una desventaja del método de la inversión en tiempo en los requerimientos de memoria necesarios para la inversión, debido a que la capacidad de memoria que se requiere es más de 30 veces mayor que para el proceso de inversión en frecuencia. Bien, como conclusiones, podemos decir que ambos métodos producen imágenes de muy buena resolución con información cuantitativa cercana a los valores necesarios cuando se mide en un ambiente sin ruido. De hecho, no es necesario invertir todas las frecuencias de los scans medidos, sino que se pueden usar solamente aquellas componentes de frecuencia en mayor amplitud y los métodos van a converger a una solución de imágenes correctas. Sin embargo, cuando el ambiente es ruidoso, es recomendable utilizar inversión en el tiempo, ya que podemos utilizar toda la información disponible en los scans medidos. Esto hace que el método sea más inmune al ruido. Pero esto implica unos mayores recursos de hardware para su implementación, o el uso de estrategias computacionales de software que permitan hacer la inversión en un tiempo viable, con equipos de cómputo no tan sofisticados. Si no se cuenta con el hardware disponible, el método de inversión en frecuencia usando control source es más recomendable, aunque en este caso se debe tener mayor cuidado en el diseño de la adquisición debido a que este método es más sensible a la cantidad de receptoras que hayan disponibles y es necesario usar suficientes transductores para que converja a una solución de imágenes correctas. Muchas gracias y quedo atenta a preguntas. ¿Sí?
Thank you, Anna, for that talk. I now would like to introduce you to the moderator of our first webinar, Professor Chris DeCourt. Chris DeCourt is a professor of medical ultrasound techniques at Radboud University Medical Center since 2015 and a professor of medical ultrasound imaging at the University of Twente since 2016. He studied electrical engineering at Eindhoven University of Technology. In 1999, he obtained his PhD at the Biomedical Engineering Group of Thorax Center, or MAS, University Rotterdam, with his thesis on intravascular ultrasound elastography. I would like to remind you again that questions can be asked in English, Portuguese, or Spanish. Questions about the speaker's research and career are welcomed, and you can type your questions in the chat box. Thank you.
Thank you, Lacey.
You're welcome.
Yeah, it's an honor to moderate this session with two very distinguished speakers. Two topics, one really more clinically oriented and one really technical development. I see already some questions in the chat. So let's move on to the first question. And the first question is for Carla, who presented the first presentation. And it's by Ivan Miguel Rosado Mendes, I think from Wisconsin. And he's really interested in the comparison made between strain in the phantom and strain in the subcutaneous tissue. Because he says, yeah, the spatial distribution of stress is not homogeneous. And will this bias your measurements? So can you tell something about it? First of all, I'd like to congratulate you with your technique where you have this phantom and that you put it on top of it. And you can use it as a kind of normalization thing. So you can compare the strain in the phantom with a strain in the arm, which is a very nice technique. But can you comment on the question by Ivan?
Can I answer in Portuguese? Okay.
Eu padronizei todas as medidas. Aqui. Padronizei todas as medidas.
Okay, so you want me to translate for you?
Ok, for me.
Okay, go ahead.
Eu padronizei todas as medidas. O próprio aparelho gera um gráfico de deslocamento e em todos os pontos eu apliquei a mesma pressão controlada por esse gráfico. Isso é importante.
Let me translate this part. So she uses standardized measurement in this phantom. And can you repeat a little bit, please? I never done this before. Sorry, guys.
O aparelho de ultrassom gera um gráfico de deslocamento e eu
and this device generates a plot so you can see the displacement.
Yeah, so I think it's really complicated to see if there's if the stress, since it's not homogeneous distributed, if that has an effect. Probably it will have an effect, at least as my impression. But as a first order approximation, I think it's a very nice technology that you have this phantom where you can measure strain and then you look at the strain just below this phantom and get an indication of at least what the Young's modulus is, because you can compare it to the strain in the phantom. I hope that answers your question, Ivan.
Yes, thank you so much.
And then Roberto Lavarello also has a question, also for Carla, because I'm looking at the questions that popped up first. And of course, you had the first presentation, so you also get the first questions. And he says lymphedema needs to be differentiated from other types of edema in the limbs, such as venous insufficiency. Typically, this is performed using lymphoscintigraphy or other techniques that allow locking of the lymphatic system. Can novel ultrasonic method differentiate lymphatic from non-lymphatic edema? Do you think that's the case?
Não existe método o Doppler ele vai medir, por exemplo, o ultrassom Doppler vai medir a circulação sanguínea, linfática não.
So the Doppler would be able to measure the blood flow, but not the lymph circulation. I think that's it. That's relation.
And looking at your results, I was particularly interested in so you're measuring the strain, and I'm not an expert in lymphedema at all, so I know it exists, but for the rest I don't know anything about what the mechanical properties are of this tissue and how does it work. Is it a kind of poroelastic material? So if you compress it, does say the water or the solution, is it pressed out or is it really embedded in the tissue? So in other words, how fast did you measure? And is there say, if you press it, do you see also changing strains in the lymphedemic tissue?
Necessary to say what? Repeat, please.
So you do your experiment, and so you measure, you put your phantom on the arm,
Yes.
and then you start compressing or deforming the tissue. The phantom itself, if you apply force, will deform with a certain rate, but the tissue below it will also deform. But do you see in time a change in this deformation? So if you deform it, then do you see the strain decreasing, for example, after some time, or so how stable
você vê a deformação quando você comprime o phantom junto com o tecido? Acho que também a pergunta é se é em tempo real.
Sim. É em tempo real e por meio de um gráfico de cores, eu consigo ver essa deformação do tecido e comparado ao phantom também, por um gráfico de cores.
And she answers that it's so it's in real time, and you can see these changes in color. There's a color map, and you can see this deformation, basically when the transducer is pushing the tissues in front of.
Okay, thank you. I think we move on now to questions for Anna before she gets bored. Again, a question from Ivan. Thanks for a very clear talk. In the noiseless reconstruction, the demonstration of the principle of reciprocity led to the conclusion that a smaller number of sources can be used without sacrificing accuracy in the reconstruction. But as you stated in the conclusion, reducing the number of sources would also lead to a reduction in SNR. Are you planning on performing an optimization for the number of sources and tune that really with the noise?
Yeah, very nice question, Ivan. Actually, we did some experiments already, and they were published. If it's SPIE, if I'm not wrong, but we didn't do kind of optimization for the number of sources. But we run some experiments, also synthetic experiments. But we wanted to search for the minimum number of sources. Of course, something that will be really more interesting is to know where to locate them, minimum number of sources, minimum number of receivers, and also considering noise, what would be the minimum number of transducers. So yeah, we didn't go in that direction for finding the optimal acquisition, but we have done some experiments to at least consider the minimum number of sources, because we noticed that was an issue in the frequency domain reconstruction. So very nice, very good question.
Okay, good that you mentioned the frequency domain reconstruction, because there's another question from Jean-Gabriel Minonzio. And he says, how did you choose the number of 31 frequencies? How many frequencies do you need? Should it be enough, or do you need more or less, or can you elaborate on that?
Thanks, Jen, for this question as well. The minimum number of frequencies was 31 to actually fit the same reconstruction as in time. So you could add more frequencies. Of course, as we increased the number of frequencies, we also increased the time consuming for the reconstruction to get the images. So we actually just select the number of frequencies that we could reach the same result as in time. So how did we choose them? We select the frequency with the highest information, with the highest value in amplitude, and then we select all the frequencies around this peak frequency where we have the maximum amplitude of the data. So we went to the 31 frequencies with the highest amplitude from all the spectrum that we could get from the scans. So those were the frequencies that we selected.
Okay, I think it's a very clear answer. And another question by Roberto Lavarello. He says, yeah, it's very nice. This tomography is really interesting. So you now presented results on the speed of sound, but you can also map, say, the attenuation. Can you comment on the potential of attenuation mapping, of attenuation images of the breast and for breast cancer detection?
We went to reconstruct the sound speed. We actually haven't tried on attenuation. That would be another physical characteristic that we could invert for. We are now doing density and velocity or sound speed. Of course, in attenuation, we have solutions that might not be actually like a real solution, and we have to be careful with those solutions and try to not get into some sort of local minimum that is not actually a possible solution. And that's why we're not inverting for attenuation so far. So right now, we are inverting using FWI, that is the interest right now. And of course, Koen is also in Delft having your laboratory trying to invert real data, and they have already done that. But no, we are not planning on inverting for attenuation in the coming work so far.
Okay, so you mentioned already density.
Yeah.
Again, I'm not an expert in this difficult methods, at least from a theoretical point of view. So can you really measure density, or is it related to the speed of sound you're measuring?
Yeah, it's related to the speed of sound. So
Okay.
it's important to say that, because when you try to invert for both characteristics, then you may get into some kind of crosstalk between them. So, or if you have information about real tissue, you can also measure density, but we can get it from the speed of sound as well.
That would be very nice if you could measure really the density independently from the speed of sound, because then with speed of sound and density, you can have a kind of parameter related to the mechanical properties of the tissue.
Yeah, and even though we haven't done that for breast cancer or for this type for imaging, medical imaging cases, in the seismic community, we have done that actually with real data for inverting the speed of sound, velocity, P wave velocity and density, and we noticed that they are really very close together. But sometimes density can be inverted very, very fast. And then due to the crosstalk, if you don't take into account the crosstalk between the both characteristics during the inversion, then you will get into troubles inverting at the same time. So you really need to be more careful and eliminate from the observations any crosstalk between the two characteristics. Do you want to say something, Koen, related to
I wanted to add something that we actually published a paper on simultaneously reconstructing density and velocity from the pressure field only. Because normally you would need both the pressure field and the velocity field, but we actually managed to reconstruct density profiles and velocity profiles simultaneously from the pressure field only.
And did you also combine it already to get a kind of mechanical properties distribution?
No, but that's just, I would say straightforward way, because it has been, so in that sense, yes, you can independently now reconstruct density, compressibility, speed of sound, and all the related tissue parameters which depend on those parameters. Attenuation we didn't include, but to my opinion, that would be the easiest one to include, because that's frequency dependent. So that's relatively easy to include. It just means a complex wave number.
But Koen, that's fantastic. If you have all these parameters and you can combine them, then you would have a kind, really mechanical properties of the tissue, which would.
Yes, and it could even reconstruct for elastic cases the shear speed and those kind of values. Yeah.
Excellent. Thank you.
Sorry for the interruption, Alan. Because
no.
Thanks, Don.
Thanks a lot. This sparkles the discussion, so that's very nice. I'd like to go back to Carla with another question, because I see another question from Roberto Lavarello, and he's still really interested in this non-lymphatic edema and this lymphatic edema. And he asked, do you expect that there are different elastography patterns in these two types of lymphedema? Because that would really be of great interest to the clinical community.
Prefere que eu traduza? Eu não estou. Ele quer saber se é possível diferenciar linfático e não, edema linfático e não linfático. Seria muito interessante para a comunidade.
por meio do ultrassom, ele vai avaliar o tecido, a quantidade de fibrose naquela região. Na verdade, não diferenciada.
Ultrasound would be able to definitely measure fibrosis. I think she's not completely sure about lymphatic and non-lymphatic. Você sabe se dá ou não?
Dá para diferenciar? Eu acho que a pergunta é com relação ao edema mais crônico e mais agudo, né?
Okay, so she's saying that if the question is about a more chronic or acute edema, completa a resposta.
A circulatória vai ser um edema mais agudo, ele não tem tanto tecido conjuntivo. Então,
in the acute edema, there is no
conjuntivite.
Pode repetir, por favor?
No edema agudo, eu não tenho tanto tecido conjuntivo.
Conjunctive tissue in the acute edema is not really well present.
Portanto, na imagem de ultrassom, como é uma quantidade grande de líquido, provavelmente daria uma imagem preta, não seria possivelmente.
Therefore, in the ultrasound imaging, you should see a not very much echogenicity in the image, so it should be mainly dark.
Thank you. Like, if you don't mind me just saying something
please go ahead, Roberto.
Sure. No, but my comment was more maybe more of a suggestion, because if one could observe different patterns in the elastographic images, that would be huge, because that would obviate the need to conduct nuclear imaging examinations, for example, when you want to differentiate lymphatic from non-lymphatic edema, because you have to go back to the lymphatic system anyway. People have attempted to do that with backscatter coefficients, for example, in the quantitative ultrasound community, with limited success only. Maybe with elastographic imaging, it can be different. And if so, that certainly should be an avenue worth pursuing. So I think that's very, very interesting. Thank you.
Então, em conclusão, assim, ele disse que seria muito interessante você poder diferenciar linfático e não linfático, e a elastografia poderia dar mais informações, inclusive imagem nuclear, se eu entendi bem, enfim.
Sim, são completamente de características diferentes, o edema linfático e não linfático. Eu acho que fica as ideias para os próximos estudos.
She definitely thinks it's a good idea, and she will investigate in future studies. And also, my former advisor is here, Adilton Carneiro, is involved in this study if he wants to step in, because I'm a terrible translator. So if you want to please translate or even speak more, please go ahead. But that's it for her answer. Thank you.
Hi, everyone. Hi, Hermes. It's a big pleasure to follow this meeting. It's a congratulations, everyone, and Anna and Carla. Yes, I'm not an expertise in the lymphedema, but yes, Carla told you this experiment was done with the support of our lab. And I remember the first question about the use of the phantom over the skin, for example. It was a good strategy to have a relation about the relative information from the deformation of the tissue. For this phantom is a calibrated phantom with elasticity very well knowledge. So you can have the relative information about how stiffness is the tissue, for example, compared to the phantom. And as Carla told, is the lymphedema tissue and non-lymphedema tissue, for example, there is a big difference in the ultrasound, sure, by scatter of waves, for example. But in our case, you have used a static stiffness, static ultrasound elastography. The good idea use a shear wave, for example, elastography, In this case, you don't have the support or noise from the handling during the examination. Anyway, it's a beginning of a very interesting research. And Carla advisor, Professor Elaine's expertise in this application, as Carla told you. But anyway, you are open for any question if I can help with some details. Congratulations, Carla, again, and for this good talk.
Thank you.
Thank you for this addition. I'm also looking at the time and we have 2 minutes left. So we had already a lot of questions for the two presenters of today. This is an IEEE Society webinar. Are there questions from the audience with respect to IEEE and what can IEEE do for you, or are you interested in IEEE? If you have any questions, we have the expert here, Paul Reynolds, the president of the UFFC Society, is also joining. So if there are questions with respect to the IEEE Society, you're also allowed to ask these questions. So probably we have to give some time if there are questions. On the other hand, I think there was also a poll planned for the end of this webinar. Is that the case, Lacey?
Yes, we were going to relaunch the poll one more time just to get a final answer from everybody so that everyone got a chance to participate.
So you can have a look at the poll, and in the meantime, if you have a question, please type it in the chat. So I think now is a good time for having the poll again on the screen. For the people that didn't fill it out yet. In the meantime, I'd like to ask a question because we have time. Anna, you have this very fascinating technique, and you say we have increased resolution. What kind of resolution can you obtain?
Well, what do you mean by resolution? I mean, the image resolution?
Yeah, or the image resolution, yeah.
Yeah, okay. So, yeah, it's in the order of the sub-wavelengths, but you will have to be careful with, of course, the number of transducers that you use in your acquisition, because that will depend a lot. And also because FWI have really complications if you don't sample correctly, then you will get these cycle skipping problems, and then you can have like a really good image, but the quantitative data is not correct. So you can have resolution in the order of subwavelengths, and well, depending on also on the amount of transducer that you use, that will give you, if you want to know that in how in the order of millimeters, or what is the exact resolution, that depends on the array that you are using, of course.
Yeah, and also of course on the contrast between the tissue, the surrounding tissue, but it must be possible to detect lesions that are in the order of a few millimeters, at least less than 5 millimeters.
Yes.
Which would be fantastic, because that's the current limit now. So 5 millimeters is already presumed to be really good. So if you can go below that, that would be fantastic.
Yeah, yeah.
That's okay, true. Thank you.
Hi, Anna. I have a question about your tomography. I'm sorry if I lost some information. I was dividing two events in the same time. But have you used a ring around of the breast, or just a flat transducer?
No, we use a ring around the breast.
A ring.
Yeah.
Okay. Okay. And
so the idea is to have the breast really resting on a surface and then embedded in water. That's the idea.
Nice. Kind of a cup where the breast is in.
Exactly, like a cup. Yeah.
Exactly. Okay. So consider the literature. you have a discussion about the efficiency of if you use a ring or use a flat transducer, for example, use the idea of a reflection image or transmit image, for example. Compare your experience. What is the best quality image when you use a tomography by use a ring transducer, for example, heavy beams applied, or just use a reflection image, for example, use just one transducer to transmit and receive the information and rotate around the breast, for example?
Yeah. Well, good question. We actually haven't done any experiments using like the flat transducer rotating, so I wouldn't know what's the answer to that question. So we have tried the idea of the ring around the breast, but of course in FWI, as long as you can measure transmitted, reflected, and scatter data, then you can reconstruct. Yeah, that's the idea. But you really need to be careful with the alignment of the transducers, because when I was in Delft and looking at the experiment, we noticed that a misalignment of just a little bit of the ring, then you have troubles with the FWI reconstruction. And that's because what I was saying before, then you need to avoid cycle skipping, and any disalignment of very, very small, even if it's very small, then you can get this cycle skip, and then you have trouble in the inversion, and you get something completely different. So in that sense, the most important thing is that you can get your alignment of your device correctly, because in somehow you have to compare that with some modeling that you do by yourself in your reconstruction program. That's the situation.
Perfect. Thank you.
Thank you.
I think we are almost to the end of this webinar. So we see the poll results. So we see quite an international community. So 70% from Latin America and 30% from outside Latin America. 1/3 is already member of the IEEE Society, 2/3 not. So please think about it. And yeah, I see a lot that they are interested in the Latin American Ultrasonic Symposium that will be held in October. So that's good to see, especially since now we have the co-chair also of this conference here, so Anna. So that must be yeah, nice to hear that 70% of this audience is interested in this conference. So that's nice. I think we are almost at the end of this webinar. We're going to close the webinar, but we're not going to close it before we have the final announcements also for the next webinar and the speaker for the next webinar.
That is correct. Thank you, Chris. We have our next speaker, which will be Ivan Miguel Rosado Mendez. It'll take place on 28th June, featuring the topic on quantitative ultrasound and obstetrics and neonatology. Thank you all for joining us for today's webinar.
Yeah, and I'd like to thank the two speakers of tonight, so Carla and Anna. And I also like to thank the audience for also the vivid discussions we had, although it was by chat and also by video, by the way. So for everybody, have a good day. For the people in Europe, have a good night. And yeah, see you soon at the next webinar. Bye-bye.
Bye-bye.
Thank you, everyone, for joining us. We hope to see you at the next one.
All right.